neutron radiation can also create secondary radiation.
Believe me, in this case, neutron activation is kind of the least of your concern. Today we're going to be looking at the most evil weapon, talking about neutron bomb. This video is by Curious Droid. For those of you who don't know me, I'm Tyler False. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
Although I've covered quite a few nuclear technologies over the past few years, there is one which I haven't touched upon, but is regarded as one of the most insidious forms of nuclear weapon. One which was parodied by the Mad magazine with the slogan, "Save buildings, not lives," and on the one hand was called the cleanest nuclear device by its creator, whilst being seen as one of the most inhumane nuclear devices.
Cleanest, huh? So the physics package is essentially going to be the same two-stage design family where you have your fission stage and then your fusion stage. The difference is how it is optimized. And as far as it being cleaner, it actually has more prompt radiation, but less residual fallout. Maybe that's what they're getting at.
Namely, the neutron bomb. When its proposed deployment was leaked in June 1977 by Walter Pincus of the Washington Post, it created a worldwide outcry that the American Carter administration were about to deploy them without a major public announcement. So what is a neutron bomb, and why did it cause so much controversy at the time, when despite the talk by the military that it was a much needed weapon, it was never actually deployed, and by 2003 all US stocks had been destroyed? Well, the neutron bomb is still another form of nuclear weapon or atomic bomb. Yes. But to give it its correct title, it's an enhanced radiation weapon, or ERW.
That's correct, yeah. The design goal is to maximize its prompt neutron output and to minimize the blast and long-lived fallout. So, lower yield, reduced fission tamper contribution, and an optimized fusion stage output.
It was created in the 1950s by one of the members of the Manhattan Project, Samuel T. Cohen, after he visited the Korean War and seeing the similarity between Seoul and Tokyo. He had also seen the devastation created by the bombs dropped on Hiroshima and Nagasaki, and in his mind he decided to create what he called the most sane and moral weapon ever devised.
Wow.
A weapon that would avoid the total devastation and long-lasting effects of radiation.
Is this one of those, it's kind of like the machine gun was going to reduce the number of casualties in warfare because no one would go up against such a terrible weapon? Is that the idea?
That the atomic bomb had shown, and yet would still provide the ultimate purpose of war, basically to kill enemy soldiers in the field. In 1958, Cohen had been investigating a low-yield, clean nuclear weapon, one which would create a large burst of radiation, but without creating a large amount of long-lasting radioactive fallout as seen in conventional atomic bombs. He discovered that the bomb case thickness made a major difference to the amount of radioactive fallout that would occur.
So that's true. In many thermonuclear designs, the tamper, which is often uranium-238, is designed to reflect neutrons, because uranium-238 is good for scattering, increase the compression, and add yield via fast fission. Because remember, uranium-238 isn't fissile like uranium-235, but it is fissionable by fast neutrons. It's just fast neutrons aren't typically what's used in a nuclear power plant. I mean, they exist, but they make up a tiny percentage of the neutron field in an operating reactor. So if you cut uranium-238 tamper mass, you'll reduce secondary fast fission, and you'll reduce the fallout, because uranium-238's fission products would actually dominate the fallout. And you're going to allow more neutrons to escape, which is really the opposite of how you design a proper nuclear reactor. You don't want neutrons to escape, because then the reaction won't be self-sustaining. But again, this is a weapon, not a reactor. So you don't want anything steady state. It's just a one-use device. But yes, this will also reduce total yield, because even though a thermonuclear weapon is considered a fusion weapon, a lot of energy does come from fission and fast fissioning of the uranium-238.
This was because the case of a nuclear weapon, which was often made from depleted uranium, and was used to reflect neutrons.
Him saying depleted uranium, so not enriched uranium. So mostly uranium-238. You've depleted your supply of uranium-235 that you would use in a reactor.
From the nuclear reaction back into the bomb's core to increase its reactivity many times. This was also the source of most of the radioactive fallout. He figured that if you used a thinner case material, most of the high-energy neutrons would escape. This would create a much lower yield weapon with less destructive capability, but it would release 10 to 15 times more neutron output compared to a conventional nuclear weapon.
So a larger fraction of that total energy would leave as prompt neutron flux instead of being captured within the weapon assembly. Again, it's the opposite of the reactor leakage fraction that you worry about in a nuclear power plant, because after all, you try to minimize it. But in these enhanced radiation weapons, leakage is the feature.
Neutron bombs were unique in the fact that the radiation radius would extend beyond the blast radius of the weapon.
And this is kind of sinister because it's the opposite of a typical nuclear weapon, where the prompt radiation specifically doesn't go beyond the blast radius at all. In fact, it usually extends out to a much smaller fraction of the blast radius. Now, keep in mind, when I say prompt radiation, I'm not talking about fallout. Fallout is caused by fission products and is carried downwind. This is prompt radiation specifically from the weapon. And depending on the yield, blast effects scale with roughly the cube root of the yield, and neutron attenuation in air, so this is an airburst weapon he's showing right here, is governed by elastic scattering, absorption cross-sections, and the inverse square law. So for low yield, say a kiloton, blast weakens quickly, but neutron flux at, say, a kilometer away can still be biologically lethal, which is the whole point of this weapon.
Even the biggest bomb, the 50 megaton Tsar bomber, had a neutron range which was smaller than its blast radius.
Yes, and at very high yields, blast scales dramatically. Neutron output does not scale proportionally, and many neutrons are going to be absorbed internally in its much larger secondaries. Larger bombs, your goal is blast and thermal output, not neutron leakage.
He calculated that a 1 kiloton bomb could release more lethal prompt neutron radiation than a much larger conventional non-ERW device.
Yeah, within certain ranges, because again, the prompt neutrons in a conventional nuclear weapon are largely used to drive fission in the tamper and increase the total explosive yield. This whole design is sacrificing yield for total neutron fluence.
He justified this use of radiation to kill soldiers because it would have a relatively small blast radius and do much less damage to the surrounding infrastructure and buildings, as well as being more humane than using many conventional weapons such as thermobaric bombs, napalm and cluster munitions. Although he was convinced in his ideas that this would be an ideal and manageable nuclear weapon that could be used as a tactical device on the battlefield, 6 presidents came and went before he could convince President Jimmy Carter that this would be a weapon to counter the overwhelming tank superiority of the Soviet Union.
Interesting, Jimmy Carter was also a nuclear engineer that went to Georgia Tech, and that's about all we have in common.
Which by the mid-1970s was deemed to be up to a 4-to-1 advantage compared to NATO in the European theatre. The problem which NATO had in the 60s and 70s was that the Soviet Union had created a huge conventional army with many more tanks and armoured vehicles. The fear was that a Soviet attack would send huge amounts of tanks into West Germany in tight formations, making them much more difficult to counter than if they were spread out. Cohen convinced Carter that this small ERW could be used to intimidate the Soviet Union into widening their tank attacks and thus making them more vulnerable to conventional weapons like NATO tanks, which were seen to be superior, and the anti-tank missiles which NATO had in the hundreds of thousands. If that didn't work and the conflict was going against NATO, these weapons could be used on NATO soil with less blast damage and residual fallout than a conventional nuclear bomb, and that they would be small enough that they might not trigger a full-scale nuclear retaliation from the Soviets. The idea was that they would be detonated above the massed ranks of Soviet armor.
Doctrine-wise, I can see this being a slippery slope, and that the gradual escalation of smaller tactical nukes to potentially using larger ones. It's kind of, where do you draw the line? But that's kind of getting into game theory and that whole modeling of nuclear warfare.
And the intense burst of radiation would produce an almost instant incapacitation of the crews inside any unprepared armoured vehicles and troops on the ground within about a 1 kilometre range. This was seen as a deterrent that would minimise civilian casualties, as it would be restricted to military targets and kept away from civilian areas. But of course, this was still a nuclear device, and although it was much smaller than the one dropped on Hiroshima, 1 kiloton compared to 15 kilotons, it still produced a blast radius of about 500 metres. And because it had much less radioactive fallout, Cohen said that it was a clean weapon that would leave the area it had been detonated over able to be used within days or less by what was hoped to be NATO troops. But the idea of using a tactical nuclear weapon against the much larger numbers of conventional armour of the Soviets was seen by many in the Western military and political leadership of the West as being one of the triggers that could bring about an all-out nuclear war. One that had to be avoided as much as possible unless there was no other alternatives.
Yeah, you have to assume the other side doesn't escalate.
The use of these enhanced radiation weapons was put into practice in the late 50s and 60s, though, as part of anti-ballistic missile systems used by...
So the idea of using these against tanks. So these fast neutrons are significantly more energetic than neutrons produced in a nuclear power. About 14 MeV from deuterium-tritium fusion. So they're highly penetrating, and they're much less attenuated by steel in an armored vehicle than gamma rays. And inside a tank, well, the people are mostly water. Neutrons scatter very efficiently across hydrogenous material, so water is actually reasonably effective shielding. But if you yourself are the shielding, that's not a good thing, because those neutrons are going to have high linear energy transfer, which are going to recoil a bunch of protons, and you're going to get a very high dose from this weapon, even in an armored vehicle. So yes, I can understand the logic flow behind designing a weapon this way, as crazy as it is.
By both the US and the Soviets. Here, high-speed anti-ballistic missiles such as the Sprint missile would be fired into the path of an incoming ICBM and detonated within about 100 metres of it. The high-energy neutron burst given off by this would cause a partial fission of the incoming warhead, with the hope of effectively disabling the weapon. Approximately 120 of these neutron bomb-armed missiles were built, and about 70 entered service from 1975 to 76 as part.
So this is an interesting idea, because neutron flux would disrupt incoming warheads by potentially inducing fission in fissile material or just damaging the electronics by neutron bombardment. So this would actually be more of a clean use case than using it on personnel and vehicles.
Of the Safeguard anti-ballistic missile program, until it was eventually shut down and decommissioned in the early 1980s as part of the Strategic Arms Limitation Talks, or SALT.
Yep.
The Soviets also used this type of device as the last layer of their anti-ballistic missile defense over Moscow to protect it against a Western attack. But how clean and humane were the claims of Cohen about the neutron bombs? The primary method of destruction was an intense burst of neutron radiation, which would be effective against any organic materials. Basically anything that was alive within the radiation radius. Atoms are made up of positively charged protons, negatively charged electrons, and neutrons which carry no charge. When a fission reaction occurs...
Interesting, him starting with deuterium. That's interesting.
In materials like uranium-235 or plutonium-239, these large unstable atoms split apart.
So one thing where it's just showing these fission events, it's not all going to be krypton-92 or barium-141. It is a spectrum with different probabilities. You refer to the old Dolly Parton curve here. You can see it's arranged with fission products centered around 95 and 135 for uranium-235.
When they're hit by a neutron. This causes new isotopes to be created and a lot of energy in the form of heat, gamma and X-rays, and the release of 2 to 3 more neutrons, which can then go on to hit more uranium and plutonium atoms in an exponential chain reaction, which only stops when the material itself is blown apart by the heat of the reaction.
Pretty good description of fission in the context of weapons, because after all, there's no operating in a cycle here.
The neutrons released are fast or prompt neutrons, usually in the 13 to 14 megaelectron volt range. This means that when they hit protons in atoms of living cells, especially hydrogen atoms in water and fat cells, they can recoil a proton forward at high speeds. And because the proton is a charged particle, it dumps its energy.
Wow, I don't know this person's background, but he's going into some pretty good detail. This is something a lot of people don't realize when they talk about neutron dose.
Very densely, causing intense ionization paths within the cell. This causes complex DNA damage, like breaking it up into smaller strands and leaving clustered lesions. It also damages cell structures and membranes and causes cell death or the loss of function. This high-energy neutron radiation can also create secondary radiation, which gives off gamma rays and other energetic particles, which could go on to create even more damage within cells.
All right, he's talking about neutron activation. That's actually exactly how we create radioisotopes in research reactors. The difference is in a bomb, flux is intense but brief, whereas in a reactor, flux is lower but sustained. So this is less likely to happen in the event of a bomb, but believe me, in this case study, neutron activation is kind of the least of your concerns at this point. The amount of dose you're going to be getting is going to render this point moot if you're talking about the effects on personnel being hit by one of these weapons. Okay, he gets into more of it here. This is an interesting graph here being superimposed on a world map. It's like, no, nothing's this big. I'm sure they don't mean you to take it literally, whoever came up with this graph, but yeah, that's kind of different.
Metals, but also including air, water, soil, and the elements in it can be made radioactive. Normally these have short half-lives ranging from 7.3 seconds for nitrogen-16, which is found in air and water, to 14.96 hours for sodium-24 in concrete and soil salts, but up to 5.27 years for cobalt-60 in steels and alloys.
Okay, and hence the term talking about cobalt-60, because you're using this on armored vehicles. Though, one thing to keep in mind is it's still going to be less than all the cesium-137 and strontium-90. Those have a half-life of 30 years that are going to be carried by fallout. So it's kind of pick your radiological poison here, but I do get the point. It's cleaner, but yeah, it's still going to have some stuff that's going to linger.
All of these would add extra radioactivity into the area. Although it's said that death would be instant for those close to the detonation, with radiation levels of up to 8 Gray. For reference, 1 to 2 Gray is usually fatal, but not all.
Okay, so he's talking in terms of Gray. Now, Gray is not the same thing as sieverts, especially when you're talking neutrons. So he's talking about 1 to 2 being almost lethal. Now, 1 to 2 sieverts, no, that's actually survivable, but he's talking 1 to 2 Gray in neutron dose. And there, your multiplication factor is anywhere from 5 to 20, depending on the energy of neutrons. And at 14 MeV, that's going to be tipping the scales there. So, assuming it's all neutrons, which in this case is what you're going to be assuming, yeah, it's all but guaranteed, even at a couple of Gray and 8 Gray for sure. Because in terms of sieverts, we're talking 20, 40 at the low end and upwards of 160 at the high end. Now, that's still not instant. I mean, yeah, you're not going to make it at that point, but it still could take minutes, possibly hours at the low end, compared to numbers like 4 to 6 sieverts being compared to what normally the instance of lethal dose is at 10 sieverts being over the course of several days to weeks. But at these extremely high doses, I will say data is somewhat limited, and a lot of it's driven by extrapolation and ranges. And at high doses, it can matter a whole lot where you get hit and certainly how much you get hit versus, like, say, the angle of the neutrons. Like, what angle were you when you were standing under this thing and which way the wind was blowing? There, a lot more factors come into this. But yeah, instant is, no, pretty unlikely.
his instance. If they were further away, the dose would be still lethal, but the effects of acute radiation syndrome could take days or weeks before death only occurred, as the body can no longer replace its damaged cells.
That's also it. So dose rate at the epicenter of the blast, but it falls off using the inverse square law. So yeah, it really depends where you're measuring this particular dose rate from.
Basically a slow, painful, and very inhumane end. If you've ever seen the dramatized TV series Chernobyl, then you've seen the effects this has.
I'm glad he mentioned that it was dramatized, because it absolutely was.
Now, this was under ideal conditions. However, in the real world, things are different. The Soviets knew that these weapons could be used, and it doesn't actually take much to add protection to mitigate for most of the extra neutron radiation. The air itself provides absorption of neutrons. This is why the range is only about 1 kilometre. Beyond that, it drops off rapidly.
Yeah, so the number he's getting 1 kilometre from is the mean free path. That is to say, fast neutrons scatter and lose energy very quickly. And once slowed to thermal energy, so in the electron volt range rather than mega electron volt range, they're way more easily absorbed. So this lethal range is finite and, again, geometry dependent, not to mention weather dependent. Humidity can affect this mean free path quite a bit.
Also, armoured vehicles can be fitted with extra materials with high hydrogen content, such as water, plastics, polyethylene or boron carbide, boronated steel or wax.
Absolutely. Polyethylene's pretty good neutron shielding. That's why spent fuel transport casks, reactor shielding, and neutron beam lines are going to use hydrogen-rich materials. In addition to concrete, the concrete reactor containment structure is hydrogenous and good at attenuating neutrons. So even a few centimeters can significantly reduce fast neutron dose. And yeah, you can absolutely harden tanks.
This could drop the neutron level within the vehicles to where it was no longer capable of incapacitating the crew. Then there is the issue that if such an attack...
Though then you get to the point where you could have, and again, this all depends on the angle of detonation, where you can have them get lethal doses, but it wouldn't become readily apparent until after the battle occurs. So it would be the opposite of this humane weapon, if there were such a thing, goal, because it doesn't stop the attack, but instead gives people horrible acute radiation sickness. So that is to say, if the tank has just the right amount of shielding and they get just that right amount of dose, that it gives them regular acute radiation sickness.
Were to occur, there will be thousands of vehicles, and they would only have to be spread out a bit more, and you would need hundreds of neutron bombs covering approximately 1 square kilometre each to mount an effective defence. Even though they had a much smaller blast radius and fallout levels.
Yeah, they're not going to change, these neutron bombs aren't going to change the warfare doctrine. And then we go back to the earlier point that, okay, if you counter with multiple neutron bombs, your enemy is going to see, okay, they're rapidly escalating this to nuclear war, so it's going to be that much easier to escalate into full-blown strategic nuclear war with ICBMs, nuclear subs, nuclear bombers at full thermonuclear size and blast rather than just the neutron bombs.
Detonating dozens or hundreds of neutron bombs in a relatively small area will probably be worse than using conventional nuclear weapons. And as it would be used
in terms
on
of escalation,
home soil, any collateral damage would be against German civilians, not Soviet ones. But the most obvious thing was that any form of tactical nuclear weapon, be that conventional or ERW, would more than likely trigger a corresponding response from the Soviets. And before you know where you are, you're into a full-scale nuclear.
So this is the interesting thing, and he's absolutely right about this. It's not like, okay, so the other side is going to say, all right, a nuclear device went up. All right, we got to figure out what kind of nuclear device it was. Was it a neutron bomb or was it a regular nuke? If it's a regular nuke, we escalate, but a neutron bomb, it's fine. No. Just going to say, nuclear detonation detected, time to escalate.
War. Although Jimmy Carter's administration said they would adopt the neutron bomb, they actually put it on hold and didn't build any. It would be Ronald Reagan's administration which actually built them and put them into production, with approximately 700 ERW devices in the 1980s. in the form of the W-70 Mod 3 Lance missile and the W-79 Mod 0 18-inch artillery shell. However, due
Nuclear
to
artillery.
the extreme political pressure from Europe where these devices would ultimately be used, they were not deployed and instead stockpiled in the United States. But during the mid-70s to late 80s, superior high-precision conventional anti-tank weaponry like the A-10 Warthog and advanced anti-tank missiles made neutron weapons obsolete by the 1990s.
Yeah, and you can pretty see how to what extent this argument was still followed about humane weapons, that, okay, the thing that doesn't give people acute radiation sickness or risk potential activation of the ground or area that you're trying to defend is an issue anymore. So yeah, I can see how technology moved away from this thing.
The last W-70 warheads for the Lance missiles were dismantled in 1996, and the W-79 artillery shells were fully disposed of by 2003. Other countries also developed ERW weapons, including France and China, but both again only developed and tested them. They didn't deploy them. Instead, they saw them as a technology reserve that could be called up if required at some point in the future. The Soviets did make their own versions, and after the fall of the USSR, its successor, Russia, in the 1990s and 2000s, worked with the US to destroy approximately 25,000 weapons. But due to the fractured nature of the breakup of the Soviet Union, it's not known if the now Russian ERW weapons were destroyed. But if they did survive and hadn't been maintained, it's unlikely that they would still work. So,
yes, nuclear weapons have to be maintained just like anything else.
I hope you enjoyed the video and you found it interesting. And if you
I did. I thought this was very well done. This is my first time watching one of his videos. But yeah, this I can understand from a pure physics standpoint, having something optimized for one specific goal, but the goal is horrific. Not to mention, it has enormous escalation risk. And to me, as a nuclear engineer, it's neutron economy applied in reverse. Because in a reactor, you minimize leakage. In this enhanced radiation weapon, leakage is the weapon. Same neutron transport equations, different intent. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.